Right, we've made it to 9 o'clock. Everybody ready to rumble? So my only job is to make introductions. So Matt Litz, do you have any slides to introduce yourself, or do you want me to give like a?
You can give an overview.
Yeah, so Matt's a data scientist engineer at BWX Technologies down in Lynchburg, Virginia. And he did his master's in data science from UVA in 2023. Obviously has an interest in computer vision, and he'll be telling us today about image classification with all these cool tools. So I'll let you kick it off.
Okay, good morning, everyone. So today we're going to talk about image classification with a lot of the NumFOCUS packages that they sponsor, like Scikit-Image, Scikit-learn, and then also discuss using those tools in PyTorch to and look at different ways we can use machine learning from Gaussian processes all the way down to convolutional neural networks. And then I want to walk you through the whole pipeline of image processing from image segmentation, to feature extraction, finally to classification. So if you're following along today, we've got the GitHub repo right here that you can clone if you want to walk as we walk through some of these examples. So the agenda today, we're going to give a brief overview of computer vision, then image segmentation, feature extraction. Then we'll walk into model development with Scikit-learn, PyTorch, learn how to evaluate some of our models with the TensorBoard, and some of those metrics to look at, and then also discuss saliency maps on CNNs. So just a brief overview. In my experience, I've worked on several projects at BWXT with computer vision. We use it to inspect parts for nonconformance. And I had to learn a lot of ground truths that I hope to can share today, and we'll walk through that whole process. So images, you probably are aware, are represented digitally in the computer as a grid of pixels. They can be grayscale, which is a one layer, or it can be RGB, which is the 3 layers of a matrix. So what Scikit-Image does is it reads the images, either a JPEG or a TIFF file or something like that, into Python as NumPy arrays. And one of the things to consider is the bit depth. It's very important as you pull these images in. The higher bit depths, you'll have more detailed information in your models, so you can look at some of those subtle variations in the data to improve model performance. So there's 8-bit, 12-bit, 16-bit, so just something to keep in mind. So the image processing tools we're going to talk about today is Scikit-Image. It's a part of the NumFOCUS suite of software packages. It's maintained by an active community and has just about any algorithm you would want for image processing. It's got, and it's constantly being updated with new algorithms. Outside of that, another good feature in your image processing journey is something called ImageJ. I don't know if you've used that before, but the latest version is called Fiji, and it's a distribution of ImageJ with a lot of good different packages for scientific image analysis on the go, batteries included. Okay, so let's talk about the image classification pipeline that we can build. First thing we want to do is we want to consider image segmentation. Let's say if we get an image, we're only focused on one region of it, we can build that into our pipeline to pull that image out and then train on it. And then from that, we can it usually goes to feature extraction. We can do that for machine learning models such as Gaussian process or CNNs. And then we go to classification. That's where we pass it through the model and perform our classification algorithm. Okay, so image segmentation. So today our first example is our problem statement here is we're going to look at mitochondria. We're going to look at images lab images that were taken that captures the part of the cellular structure, And so one of our goals is to remove the mitochondria from the image for classification. And here's a little blurb if you learned this in high school and what mitochondria is, but it's a good opportunity because as you can see in this image here, there's different textures, different contrasts that would lend itself well if we can modify this image so that we can pull out the mitochondria, which are these little circular structures right here with the cellular walls. This data set is pulled from MitoNet. It was founded on GitHub. It's a collection of images and also a CNN that was trained specifically for this purpose. So we'll be using those images today. So the typical order of operations when you segment an image is you go through different steps. First is like pre-processing. So you want to reduce the noise in the image, do some contrast enhancements so that those different layers can pop out. Thresholding, you want to separate the foreground from the background. You can identify certain regions that you want to pull out of the image. That's the whole goal, so that we can identify what we're looking for. And then there's morphological operations. Once we've brought it to that binary space, we can do erosion, dilation, some of those operations to refine the boundaries of our segmentation. So just to walk through some of the different tools, that first step is histogram equalization. So if you consider an image, it's a matrix, and this example was pulled from the Scikit-Image API. But what our goal is to increase the contrast between pixels in an image. That's going to help us in our classification. Histogram equalization. If you see this image here, it's very tightly grouped, and if we expand this histogram out, we can get a richer representation of the data in the image. So there's different algorithms for that. One of the biggest ones that's typically used is the CLAHE algorithm, adaptive equalization. It focuses on local regions of an image to pull out those contrast regions. That's one tool in our toolkit. Another thing is gamma correction. It's a non-linear operation that adjusts the brightness across the image. It also helps with improving contrast. So that's our first step. Another step in that pre-processing operation is filtering. So if we look at our original image, there's a lot of artifacts in there that we want to sort of smooth out so we can clearly define the regions of the image that we want to apply, that we want to segment out. So one of the first things is a Gaussian blurring operation, which takes a filter and smooths the image out with a Gaussian kernel. So that, and you can see here it blurs the image and kind of gets some of those artifacts and makes it more homogeneous. Also, there's bilateral blurring. That's a really good toolkit. The Gaussian smooths out the images in all directions. Bilateral helps retain some of those edge distinctions when you perform the smoothing operation. So the next step after we've pre-processed the image is to apply some thresholding to the image. It's used to create it separates the image into the binary, or sometimes in the multi-Atsu case, multiple layers of segmentation. So it looks at the histogram, and you want to separate the high peaks at the local minimum that maximizes the variance. So that's the Atsu method, which gives us two regions. You can see this image separated into the black and white region. And it found like that local minimum right there to do that. The multi-Atsu is similar, but it produces looks at multiple minimums to divide the image into distinct classes, and we can use these methods to our advantage as we go through the segmentation operations. Okay, and then the next one is morphological operations. After we've taken it to that binary step, sometimes we want to close boundaries. So we can define that region of the image that we want to pull out. So we've got the principal operations with binary image morphology is dilation. So it enlarges regions in that binary image. Erosion, it shrinks the regions. Opening, which is a combination of erosion followed by dilation, and closing. So if you have a gap here, it expands the region and then erodes it. So that's an operation, two-step operation. A lot of times though, you have to define a footprint, which is used to help define the thickness of these operations, and it's in Scikit-Image's morphology class. Okay. So at this point, let's walk through. We'll do a demo. Okay. So this is a image segmentation demo. So first thing we want to do is let's read in our image. Well, first we want to load our packages. So NumPy, Pandas, Matplotlib, Scikit-Image. So let's bring that image in that we want to look at. There's our mitochondria. Okay. Now first let's try to clean up those images we talked about. Equalizing the so the first steps we want to do is let's try adjusting the gamma, and then this whole operation you have to tweak the settings to really achieve what you're looking for. So we can run it here, and you can see the gamma. We could have tried the adaptive histogram, but let's go with the gamma, the gamma cleaning. It shows what the two different filtering operations performs, and in this instance, we can see that the adaptive histogram equalization produces the most contrast between the two different images. So that's the one we'll choose. So now let's try to perform the Gaussian blur operation. So that we went with our histogram equalization. Now let's blur that. So remove some of those artifacts so that our thresholding can pop out those different regions of the image. Next, let's do our multi-Atsu threshold. So if we run that, it's identified 3 different regions here that it segments out. And you can see our mitochondria is in this blue region right here, and the cellular structure is here, and then a third layer is found right there. So it found those parts of the image that shares those characteristics.
Question.
Yes.
What would happen if you were running this multi-Atsu threshold without doing the Gaussian?
You would see. So you see this fairly uniform section there. It would be very speckled. So we want to remove it. So and after you pull the image, let's say the mitochondria out, you would see a bunch of speckles in that region. So a lot of artifacts would be retained in that image.
So when you do the blurring, are you just smoothing, like mathematically smoothing between pixels?
Yes. Yeah, with a Gaussian kernel.
Sure.
Okay. Any other questions? Okay, so even when we did the Gaussian, there's still a lot of little speckles within that region right there. So Scikit-Image has this really cool function where we can remove small objects from that region. So let's test that out. So what we did here is a 4-step operation. We first applied the Atsu threshold, which was the binary thresholding, and it principally found this cellular region, missed the mitochondria, and we've got this region here. The multi-Atsu was able to identify, the mitochondria region. That's what we want. And after we apply this large remove small objects, we performed the multi-Atsu. Now we were able to remove additionally those small artifacts in the image. So we've really honed in on the mitochondria that we're looking for. And so now we can apply that to the original image, and you can see we zeroed out the regions that we're not interested in, but we retained the mitochondria regions, except this part. We don't really know what that is. Hopefully we'll get to that in a little bit. So this is one method to remove it. Okay, so now let's look at utilizing morphological operations. So here's another image of mitochondria. This is a very messy image. There's not a lot of contrast here, so this is a challenge. So let's start off with some of our cleaning operations. We want to do an adaptive histogram, and then the Gaussian blur. So that really helped out isolating the borders of the cellular wall here, which we're interested in, while also sort of blurring this region right here that we're not interested in. So so next let's apply the multi-Atsu threshold, as well as removing the small objects, and it really dialed in the borders of what we're interested in. But if we were to subtract this from this mask from the original image, we're just going to have the cellular structure. We need to expand that region so that we fill in the gaps here. So when we apply our mask, we'll have that image texture that we're interested in of the mitochondria. So next let's do the morphological operation called dilation, where we're going to we assign that footprint and you have to tweak these sizes here and use that to expand that region. And as you see here, it dilated out the regions of interest while excluding a good proportion of what we're not interested in the cellular wall. And so now let's apply that mask to our original image, and you can see we've retained a lot of what we're interested in for later classification. Okay. Any questions or yes?
So those footprints are just loaded into the library, like they have different shapes and sizes?
Yes. There's like a disc shape, there's star shapes. And it's used to expand the binary region of that image. So yes.
So thinking of like on the broader process, we're first segmenting the image, and then we're gonna use this segmentation to classify and identify where the mitochondria is on a different picture.
Yes. Yeah, we're excluding the parts of the image we don't care about, and then we can pass it through. We would be able to pass it through a machine learning algorithm. Yes.
Sorry, I was a bit late, but is the original image single channel?
Single channel grayscale. Yes.
Do you thought about, or do you know how to deal with multiple channels if there might be pixel differences?
I typically take it to the grayscale, but I haven't really worked with RGB in that regard. It definitely complicates things. Okay. So now those are traditional segmentation methods that you can use. So if we want to go to a different more advanced method, we could use Gaussian mixture model on the segmentation on the image. And so let's load our image here. And similar to last time, we go ahead and pre-process it. We perform the histogram equalization, then we blur it. And then we can use a Gaussian mixture model to find out regions of the histogram that we could define as different classes in the image. So I think it uses the KL divergence, it calculates that. So going into this, we can look at this image and say, well, we see about 3 classes there. We're interested in the contrast yields itself to saying that there's 3 classes there. That what we're interested in, the cellular structure in this background here. So you set up your estimation of 3 components and apply the Gaussian mixture model. You break the image apart into a single array, pass it through the model, and reconstruct the image. And let's see what it found here. So that's pretty decent. Definitely found the mitochondria, found the cellular structure here, but also found this region. So that's similar to the multi-Atsu. So it's a good tool to have. Still, this little region right here is not what we don't really know what that is. We're concerned about the mitochondria right here. So let's look at another method. I think this is a relatively new feature that Scikit-Image has released. It's called Weka segmentation. And what it does is it applies, so we would define regions of this image and train a random forest classifier to learn the features of that image and then assign different classes to that and segment it out. So that should help us get this unknown cellular structure right here. So let's read in our image, apply our pre-processing, our blur and segmentation, equalization in the blur. And now let's assign regions. So we have to look at regions that we're interested in. So we know that this is a region, this is a separate section, this is the cellular structure. The mitochondria is in this region. We're definitely interested in that. That's our target. And then we don't know quite what this is, but let's just assign a class to that. So we've got 4 classes now. And if we want, so now we assign our random forest classifier and classify the regions of that image that we defined. And let's see how it performs. So here we go. We're finally able to segment this out. We can apply our mask to remove these regions that we're interested in of the mitochondria. So I just found out about this from a colleague at work. It's a really powerful segmentation tool. Yes.
When we're assigning the classes, do we do it by hand?
Yes.
Or, so those squares that you had like a little bit before, we were defining these are like the XY coordinates of the different areas that we're interested in.
Yeah, that's correct. Yes.
And we're saying this is this part, this is this other part.
Yes.
Okay.
Yeah. So the understanding is if you have multiple images, the expectation is that these regions would be similar on all those images. So once you train it on that, you apply it to your suite of images. Now you've got a pipeline that you can, as new images come into, you can extract the images out. Okay. Any more questions? Okay. So that's our segmentation portion of the pipeline, and all this can be automated, as you deploy this in production. So now let's talk about feature selection. So now let's look. We looked at mitochondria. Let's continue the trend of looking at biological features here. So there's 2 different classes of viruses out there called an adenovirus and an influenza. They have similar symptoms, but they often pose different levels of severity. So it might be good for researchers to understand, maybe use binary classification to separate which one is which. So I found a data set online. It uses transmission electron microscopy (TEM) images that was used to generate these images. And the top region here is an influenza model. It's got a unique texture with a sort of a border around it. And down here, we've got the adenovirus also has a really unique, pixelated pattern here that is, it's a texture that we can definitely leverage to generate features to insert into a machine learning model. So our job here is we're going to try to perform binary classification on these, but we first have to extract features. So commonly, features derived from images, typically you can look at the mean of the matrix, calculate the mean of the image. You can calculate the variance of the image. But we can also do something where we can extract textures. And it's gray level differences between the regions. So you can see different textures in the structure of the image itself. So we can build features that we can quantify that texture in there. So it's often they're defined by the size of the area where the change occurs, directionality. And if we can quantify that, we can get additional features to build a machine learning model. So two of the texture feature algorithms I'd like to bring to your attention is the GLCM and the local binary patterns. These are algorithms that are within Scikit-Image. And some of the textures that you can extract from that image, we talked about mean and variance, but also contrast, dissimilarity, homogeneity, angular second moment, energy, and correlation. So those are features we can feed into them. We can calculate their statistical features. We can fit into the model. Another really good feature detection tool is local binary patterns. Compares each pixel within its neighbor to its neighbor, and builds a histogram of these values as a feature vector. So that's another way to quantify textures. Okay, so next I want to talk. So before I go to the demo, let's look at the first model that we're going to use to build to extract these features. And is anybody familiar with Gaussian processes or Gaussian process classifier? Okay, great. So that's a powerful tool that we can use to take our features and train, to discriminate between the adenovirus and the influenza. What's really powerful about Gaussian process classification is also outputs an uncertainty. So convolutional neural net doesn't provide that sometimes, but you can calculate it. But the uncertainty that the GP produces is very, very powerful for your classification purposes. We're going to use Scikit-Image's GP tool today, but also there's another package called PyTorch that utilizes utilizes PyTorch as the autograd function in its optimization structure. So I definitely recommend that. It's got a real expansive library of Gaussian process tools you can utilize. And then also this lecture here, recommend watching that. So the pipeline that we'll build today is we're going to take our training images, we're going to build a data frame of the features, pass it through the GP, and then later on after it's trained, we can pass test images and then perform predictions on our test images. Get to that in a little bit. Okay, so let's go ahead and walk through the Gaussian process classification here. So first, let's bring in our packages, NumPy, Pandas, Scikit-Image. And we've got a function here that will pull in our training set and our test set. And we're going to take our images, convert them into a NumPy array, and then build another array of the images. So it's a three-dimensional array. So let's load that. And let's take a look at some of our images. Here's influenza, adenovirus. Those are some of the things that we look at. So now let's walk through building, extracting our features from that image data set. So we're going to loop through that NumPy array that we built. We're going to apply equalization, and then for each image, we're going to calculate the GLCM, and then from the GLCM, calculate those statistical features such as contrast, correlation, energy, all that. We also calculated mean and variance up here on each image. We're also going to calculate the local binary pattern for each image and return those as an array of features. So let's run that. So this will be applied to our training set and then our test set. Okay, and then the next thing we do is we're going to build a data frame just to understand what our feature set looks like. So here's the output of the data frame. Okay, after that, we want to normalize and standardize. As you see here, you have different levels of the mean and variance. It's dissimilar to the other features in the data frame, so we want to standardize, perform a normalization, and then a standardization process of all the features. That's going to help us with our model performance. Okay, data frame here. Okay, so now the next step, of course, is cross-validation, five-fold cross-validation. That's going to take a while. GP is very computationally expensive, so we're going to skip that step, but the code's there for that. So now let's train the model with the Gaussian process. So what you have to first assign a kernel to that will be used as the covariance function. The length scale for each one of the features you have to, so we've got 16, I believe, total features that we're going to feed into the model. You have to assign in the radial basis function a length scale for that. We assign our kernel, and then we fit that standard. So the next operation is that we fit the GP with the standardized data as well as the binary data that we generated with the labels, and calculate that. That's going to take a while to run. So the next thing, though, I wanted to, so if we want to learn feature importance with Gaussian processes, does anybody have any questions so far? Okay. One thing, as opposed to an ensemble method with random forests, one of the things to consider is feature importance. So the Shapley method is a way to examine the output from our results, and it's a game theoretic approach that will assign. It looks at the mean value generated from that Shapley analysis, and it gives a quick overview of the features that are important within our classification model. So the really good thing about that is that once we've identified the main features, we can exclude the other features from and just focus on those, and that could improve model performance as well as the computational overhead. So let's go back to, we're still running the GP.
Can I ask a question in
Yes.
the meantime? How much data do you have in this?
I think about 200 images per class.
And you have 16 features you're doing Gaussian processes on, right? At what point do you start worrying about the curse of dimensionality? So with Gaussian processes, you're learning a distribution over a 16-dimensional space. And with only 200 data points, that could be wonky. Have you thought about it, or do you know if at what point does it become a problem?
Well, that's a good, yeah, dimensionality is a key issue. In this data set, I haven't encountered that, but definitely with the feature importance, you can reduce the number of features. It's something you want to consider to avoid that overfitting issue. Okay, so after we ran that, we've got really good results here of our classification report. So Scikit-Image has a function in there called the classification report. It prints out the principal metrics that you want to look at when you do image classification. So precision, recall, F1 score immediately comes out. And we've got really good metrics here. These are the things I typically look for. After we've trained that, we can see here the Shapley values that was ran to identify feature importance. So contrast to similarity, the local binary patterns here. We could exclude a lot of these features and just focus on these and get similar model performance, reduce our computational overhead, then also reduce that potential overfitting issue with dimensionality that was mentioned. Here's a further breakdown of those Shapley values. Okay, so now let's take a random sample from the original data, from the test data set, and see how it performs. And you can see here, does fairly well within the Gaussian process to identify the issues. I mean the different images that we have. So any questions? Yes.
For the Shapley values, are those just determined by leave one out? Like, are they just going through each feature and leaving one out to see if it affects the?
Yes, that's exactly it. Yeah, it's a game theoretic approach. I don't know too much about the algorithm itself, but I think it cycles through the features. Okay, so the Gaussian process. Let's say that it's a machine learning method. It's really, if you don't have access to a GPU, this is a really good method for classification that you could examine. Okay. So now talked about our key performance metrics to look for with classification. Let's go to PyTorch. So I wanted to take, using that data set, look at implementing PyTorch with a CNN, then also with transfer learning, because PyTorch has a reputation of being a difficult framework, and a lot of people use TensorFlow, but PyTorch is really accessible. And it's really becoming the industry standard. I mean, all the NLP frameworks are the back end is PyTorch. So, and then also if you have a Windows machine, I think TensorFlow has stopped supporting Windows operating system. So PyTorch is your only option if you want to implement a neural net. PyTorch, it gives you a really hands-on understanding of what's going on in a CNN. PyTorch Lightning is a fairly recent attempt, I think, to make PyTorch even more accessible. It has some of the built-in classification metrics within the Lightning framework. I definitely recommend trying that out. In this simple example of a CNN, we're going to load the images we previously looked at. We're going to set up our dataset class, data loader, define our architecture, do some image augmentation, You'll walk through a training loop and then evaluate on random images. And then monitor performance with TensorBoard. I don't know if anybody's used that before. That's a really powerful tool to look at your accuracy, your F1 score as you train your model. Okay, so let's okay. Binary, okay, so let's start off with importing our libraries. So we're going to do a simple CNN. Some of the principal libraries you'll need is Torch Vision. We'll use some of those metrics to evaluate model performance, TensorBoard, and then this step right here says that if you want to set your device to your, if you have CUDA installed, you have a GPU on your system, use that. That's going to definitely help performance. But if you don't have that, let's just use a CPU. So let's load that to and we're using the CPU. So this is going to take a long time to converge. I want to take a coffee break here. So let's follow up with loading. Same function we used in the past. Let's load our images from the folder. Okay. Okay, now we've got the dataset class. So this is how PyTorch manages batching the images into the model. First define what we've got is images and labels. So we're going to define our image labels object here. We have to do some manipulation that as we load in those images, we have to convert them into the labels. We have to convert them to the Torch data type. It's very critical to do that, and also keep in mind if it's on the CPU or the GPU. In this case, everything's going to be on the CPU, so we don't have an issue. Next, we define this transform operation, which we define later on in the process. That's for image augmentation. This defines the length of our images. This function which assists with batching, and this is we're getting the different items here, the images and the labels, to bring them into the data set. So here, next let's define our, okay, let me execute this. Okay, let's define our architecture here. So we're going to do a simple sequential block here where we go through a convolutional 2D. We start out at 32, set our kernel size and our padding, do a batch normalization operation. We do a ReLU activation function, and then do some max pooling. So we do that 3 different blocks there, and we pass through with an adaptive average pool. Our fully connected layer, we have to bring it up to 256. We have a dropout layer here, and for the binary classification, it's critical to have that as 1 because it's either going to be, that's the output of the probability. And here's our forward function. So let's define that. Okay, so now let's define our training loop. This is a function that's going to take in our model, our training loader, which are data loaders that we talk about later, the different criteria, the optimizer that we use, the number of epochs, and now we've got a function here for TensorBoard where it's going to log our metrics as we run the analysis, as we run the model training. We can walk through, okay, the first thing is our epochs. We're going to cycle through the number of epochs that we define. Then we set the model to the train setting. So we initiate the training operation. I'm going to go ahead and get this started. started down here. Well, I'll do it in a little bit. So, okay. Next so here's the step where we start bringing in our data set. We load our inputs and our labels. We send that to the device. That's important if it's a CPU or a GPU. We set our we zero the gradients with the optimizer. We perform the forward pass with our inputs and set our loss criteria, which is binary cross entropy, and then we do our backwards pass through the neural net. We calculate our loss, and then we also have a validation set that we separate out from the training set earlier on, and we perform our validation metrics. And this little block here, we include the TensorBoard writer, where we can write our TensorBoard epoch loss, our accuracy, precision, recall, capture all those metrics into TensorBoard. Okay. Our next step here is augmentation. So I mentioned up earlier in the dataset class that what's really good is we can augment our images. I'll pull that up. And so that assists with, so as opposed to our previous example where we're pulling out metrics, single values, we're going to send the entire image into the CNN. And so as the convolutional performs the convolutional operations on the image, we can adjust the images that are coming in to hopefully improve accuracy as new images are fed into the model in production. So some of the common augmentation techniques that are used is the random crop, random rotation, the random resize crop, and you can see those operations being performed. This is performed. You want to do this you want to have two different transform functions, one for the training set, and then one for the test set. And just in case you're wondering, so as you build your augmentation pipeline, we'll want that. So this is going to be applied to every training image that is passed through the pipeline. So the first thing that you do converts it to a tensor, and at that point it applies all these different operations and then normalizes the image at the end. Now, as opposed to the training set, we're just going to take the training set as it is. The only operations we need to do is to turn it to a tensor and then later normalize it.
How do you select mean as the transform for the normalize? How do you select your mean and standard deviation for the normalization? Like, or is it just is that just what's out of the box?
Typically just 0.5. I mean, that levels the whole image out. So you can experiment with that. That's very critical later on in transfer learning. We'll talk about that, because if you do transfer learning, it's expecting a certain normalization scheme that it was trained on. But we'll talk about that later. Okay, so let's apply the data augmentation. Okay, now let's build our data sets. So we're going to pull our training images into that data set class that we previously talked about. Here's where we define that we want to use the different train transform or a test transform that we previously defined here. Let's split our data into training and validation. So we're taking the training population, splitting that, and having a validation set out of that. And here let's create data loaders. So batch size, this is a metric you want to tweak. Typically 16 or 32 is a typical batch size, but that can definitely affect model performance. Next, we create the data loader class. This is going to help with our batching operations. Now, if you have a GPU, the num workers, that is parallelization. So you can assist your training, lower the time to train by setting the number of workers. Since this is a CPU, we only had 0, unfortunately. We also here assign our batch sizes, and then you can see here shuffling. So as we train the data set, that it's going to take a random population from your training data set, it shuffles it. So it's not going to be in the order that it was loaded into your NumPy array. Okay, let's define that. So here, after we've set all that groundwork for our data sets and our model, let's initialize our model, initialize the class, initialize the loss function that we're going to use, as well as the optimizer. The atom optimizer is the most common, effective optimization that we use. And then after we do that, we want to send it to our device, which is, in this case, it's just a CPU. And here's the model framework that we've generated. Okay, next let's establish TensorBoard, where we're going to set up a run ID, and this is going to log our cases. So as we adjust parameters and as we tweak our CNN, we can log that to TensorBoard. And we also create the directory that we keep our runs at. Okay, so now let's start the training process. The train model function here. We pass our model, our training data set loader, the validation loader, the criterion, the optimizer, and the number of epochs that we want to train on. So let's start that out. So this data set is so well behaved, you only need 5 epochs to find to successfully classify. So has anyone worked with? Oh yes.
So this particular implementation, you're applying all of your augmentations to every single image. There's no original images retained in the data set. Is that like convention? I mean, is there any benefit to trying to keep copies of both, or
I've been concerned about that. I've questioned that myself. Yeah. It seems to be practice that they apply the augmentations to every image.
Yeah.
But sometimes, I don't agree with that. I think it's good to you can assign a probability of your. There's a way to do that.
Yeah.
That you can split out.
So you can like have each augmentation be like 2% or 20% probable of happening or something.
Yes. Yes. I think that's more prudent to do that. Okay, so as we're training, let's look at TensorBoard and see what it's so VS Code has an integrated TensorBoard support. So let's launch that, and we can now look at some of these metrics real time. And so this is an embedded application within. You have to install the TensorBoard package, and what we're looking at here is the loss, as well as the metrics of accuracy, F1, precision, and recall. And on the left side here, this is the run name that we generated. So you have to. I think we're still stuck on. So we're at the training. So now you can see it's logging our metrics over time. After we run this, we'll walk. The next thing we'll do is we'll perform testing. We'll shift it to the evaluation mode and evaluate our images. And then we'll talk about something called a saliency map. So what that does is, this is a really cool way. After you get your metrics, you can also pull samples out of your training set or your test set, and look at what the CNN, what are the features of your image that the CNN actually was most influenced its prediction. So, so this is very helpful for understanding model decisions. Is the model working properly? Is it finding the features that we're concerned about? So as you see this bird right here, you know, it successfully identified. It's looking for features like the wings, part of the bird. So we'll run that and see how it performs. Almost finished. If you look at our metrics here, it's out of the gate, it's really high. So another good thing about TensorBoard is it logs your, so you can, as you change your parameters, you can go back in history to see how things have changed. Okay. So now let's run it on the test data, and we'll print out our classification report. Really good metrics. And so now let's take like our previous example, let's take a population of the images and let's generate a saliency map to see which part of the virus images it identified. So here you can see the influenza. It's capturing, you know, some of those features there to correctly classify that. Also the influenza, it's getting that perimeter where those tentacles are. So, and here's the adenovirus, you know, it's finding that pattern within the texture of the TEOM sample. I mean, I guess that's molecules that form the structure of that cellular structure. So, any questions or? Okay. Okay, so our last tutorial here I wanted to talk about was transfer learning. So that was a simple CNN that we generated, but typically in practice, what people do is use these pre-trained models that were trained on ImageNet or some of the huge libraries of images. You know, there's DenseNet, there's ResNet. We're going to talk about ResNet today. So I always wondered, you know, how does this really work? I mean, it was, you know, you have such a custom application. How does this model work to, if it, you know, what you're looking at if it wasn't trained on that model? But you can think about it that the images, the quantity of images that it was trained on, it's seen so many, you know, image types, image opportunities that it effectively captures the image world. And that's a new way to think about it. So, but there is a way to fine tune these models. So it was so as the ImageNet library was, and it created the weights for the ResNet 50. You can fine tune it by freezing different layers. At the top of the last layer, you can unfreeze that layer. So as you unfreeze it, it becomes the weights in that ResNet model can be trained specifically to your application. So that can even boost performance. And you don't have to. Basically after that, you can just import ResNet into your framework, and you don't have to go through the arduous task of building this CNN architecture, which is very difficult, just to see if it works well. So the transfer learning is really a really effective way to do that. Okay, so with the thing I wanted to mention with transfer learning is it retains a lot of the framework that we just built. We would load the images here, and then so this, as opposed to the CNN architecture, we would define the ResNet binary class, a ResNet class. And instead of having to define the different layers, the convolutional net layers, you can just import ResNet 50 as it is. But this model was defined for multi-classification. So since we're using it for a binary application, we've got to adjust the layers in the ResNet model. So what you want to do, the output layer, you want to assign that to a feature of 1. So that's going to give us our binary option, during our classification. Okay, and basically you would keep the training and test loop the same, your augmentation's the same. I mentioned earlier about freezing. As you instantiate your model here, one of the things you want to consider is you want to unfreeze the last layer. So that's really important because that's what you're going to be training, those weights in that last layer. And another thing to consider is the optimizer here. You want to set your learning rate lower for transfer learning. I think that's an acceptable practice. And then you would train the model, and there's a salience map for the output for that. I'm not going to run the ResNet 50 model. It's a huge file to load to the CPU here, so you really need a GPU for that. So just things to consider when you're training a CNN for that. Any questions with transfer learning? Okay, so I think that's the end of my talk. Hopefully I walked you through the whole pipeline here of classification. Hopefully you can find some, take something away here as you build your pipelines. A lot of this is designed for, creating that production pipeline to pass through images and then deploying it to production. You can automate the whole thing. And as new images come in, let's say you have an inspection process or a marketing website, as new images come into your pipeline, you can effectively improve your model over time by running it periodically. So, okay, finished a little bit early. Any questions? Yes.
I have one question. So you showed that image of the saliency map
Yes.
with the bird.
Yes.
That was kind of nice. Looked intuitive, that result.
Yeah.
And then when we looked at yours, they were a lot more speckly. It's kind of like less intuitive how you're going to get any interpretation out of your saliency map versus this. Is that typical? Have you seen something like that, or do you have an interpretation of that?
I noticed that you can see some like this. This is the transfer learning, and actually the CNN itself, it performed a little bit better, identifying different features there. What I'm thinking is if we just trained it in 5 epochs, I think if we further train it, I think that would clear out, make that grading a little bit better.
The other thing I noticed in these last 2 examples is it looks like there's almost like a rectilinear pattern in there that I don't see in the original image, which looks like some sort of artifact.
Yes, I noticed that too.
I would also
That yells JPEG compression to me. I don't know about anybody else, but it could be something else.
Okay.
Let's say to visualize this better, I would maybe reduce the color range because it goes up to red goes up to 0.08, but you don't see any red. So it seems like most of the values are at 0.03. That might help you see it better.
Good, that's good suggestion.
Can you talk a little bit more about classification cases where you may have a very large number of potential categories? Say for instances like or use cases like tagging. Say I have a big library of images that I want to tag based on some list of categories where the probability of each image having a category may be quite low. Are there any pitfalls to be aware of as we expand to a large number of classification categories?
So in that regime, you would go to multi-classification. Obviously, data imbalance is an important thing. You want to have good number of samples to train from. Something to consider. You'd have to adjust your architecture, your criteria, your loss function would have to be changed from the binary to cross entropy. So definitely things to consider.
And do you think, I guess depending on the number of categories, like if you had a problem like that, would you consider training a number of like single tag classifiers and then running them sequentially on your images? Be like, is this a bird or not? And is this a dog or not? Or jump straight to like multi classification?
You're talking about pre-labeling or?
Yeah. Or like image tagging.
Yeah, you definitely, you would use the labeling. I mean, this operation here, you'd have to have a separate algorithm to do labeling earlier in the process. But this framework was just built for, in your folder structure that we have here, it was predefined as the label was the folder itself. So you could build an array to define the labels and then match it with your array. Yes.
Would you be willing to share a link to the slides, like push it to the repo?
Sure.
Yes,
Yes, I'll do that.
Right.
Is this since I was kind of late here, apologies for that, but is this code like on a GitHub or anything?
Yes.
Okay.
Yeah, the GitHub repo is got a QR code right here that you can use.
Okay, alright,
It's on the schedule
thank you.
also, yeah.
I might have missed a detail about the transfer learning. When we talk about there being a pre-trained data set, I assumed you meant a pre-trained data set on the specific images of the bacteria or the diseases. No, it's just a pre-trained data set of, it's like a general, so how this might be, so you applied a general model to a specific example, or did you somehow narrow down the, I am a little bit turned around in terms of how it was doing image classification on a specific set of images for a specific feature that we've defined, for a specific outcome that we defined off of the general model. So I'm just like, I don't know if you could talk a little bit more about that potentially.
Yeah, that's
I feel like I'm missing a conceptual step here. I apologize.
okay. No, that's a very good question. I've thought about this myself and recently just had a better understanding. So like ResNet is like trained, I think, on ImageNet, which is a huge population of it's a public image data set. It's trained on that, and the idea behind transfer learning is that it's the population of images is so great that it's going to capture just about every image that the structure that's in the outside world. It's going to be captured within that framework. So out of the box, if you've got a standard image that you're trying to classify, like a computer, a dog, a cat, or something, ImageNet, out of the box, it's got it. But in those cases that you have something extremely specialized, like this virus, that's where we've got to unfreeze layers in ResNet. So we gotta unfreeze like the top layer. And after those weights that were predefined, as you unfreeze that, you can train those weights again through our training process. So those would be specifically designed for your training set.
I see. So presumably, like the ResNet model does have a significant amount of bacteria imagery or what have you, but then you are importing specific labeled cases for your project and then modify the finest detail slightly to get it to the specific use case.
That's exactly right, yes.
Thank you.
Yes.
Is it that the data set, because you can think of a case of transfer learning where you're trying to classify something that's not in the original data, just like for microscope images, there may not be microscope images of something exactly like what you have in there that you're testing on. Is it the case that maybe your virus shares some features with like a dog or a bird or something like that, and it's picking up and you're tuning those features in the model? Is that also?
That's the idea
Okay.
behind ImageNet.
Do you mind if I expand
Yes,
on that a
yeah.
little bit, just from my experience? When you initialize these models initially to random numbers, you can think of all these layers as responding to like a different kind of static on the TV, right? And the hardest part of training in some ways is getting those lower layers to have some sort of reasonable features, right? They don't get to look at a lot of the image. They just look at this little clump of pixels. And you're like, okay, well, okay, what's important? Well, edges are important. What's important? Corners are important. And now the next layer gets to use those very, very local, low-level features to think about what bigger features can I build. And so by training on just like images that are of the real world and not of static, you can train up those low-level features. And that's like all the yellow stuff on this slide is like features like, edges, spots, like these kinds of low-level things. And then all you have to do is unfreeze that kind of top layer and you get to benefit from all of that pre-training. So like you could unfreeze everything and say, I'm gonna build the best model for cell networks, and maybe that would even perform better if you had all the time and all the GPUs in the world. But this is a great way to like accelerate that process and get the benefit from that initial pre-trained model.
Well said, thank you. Yes.
Can you talk a little bit about how you select a pre-trained model? So say you're gonna go fine tune on adenovirus or whatever it is. How do you go about selecting a pre-trained model that you're gonna fine tune?
There's leaderboards out there that indicate model performance. So there's a whole suite of different models out there. I think the Keras website has a list of like ResNet, DenseNet, WeNet, and you can see the performance of each one of the models. So you can pick the top performing model. Yes.
For the Gaussian processes, do you use like a weekly informative prior ever to like speed it up, or like image data too unstable for that?
In the algorithm, you don't assign the prior. I think it's the kernel is you assign the kernel for the covariance function. There's different options for that, but I think it's it's a Gaussian prior. So multivariate.
All right, if we don't have any other questions, I think we can break and chat. The next, there's like a break built in too, so the next tutorial starts at 11. Thanks, everybody.